Dear friends and dear colleagues, have you ever seen a rocket flying? You can also build a rocket yourself. In a previous presentation, I gave some instructions how to do it in the simplest way, but you can look also for other channels in internet or also on YouTube. And the most simple rocket we can buy or we can build is a water rocket. So we are referring to this type of rocket in this presentation. But as far as we are scientists, we want to understand what this makes a rocket flying, what's the reason for getting higher or less high. And we are doing it as usual by means of our beloved friend, the physics. Our approach is definitely the same. So start with the observation, what is happening. Then we observe the rocket flying and we call the physical principle behind to develop a model, and then finally we check if the model can explain the reality. So there are 3 steps. Let's see together.
How is made a water rocket? There are 3 parts. First, a shell, then the air inside, pressurized, and the water which is lost. The air is pushing the water out of the shell towards bottom, and the rocket is moving towards up. On the right side, there is a picture of a water rocket made by the plastic bottle with its pressurizing device, a hose, a garden hose, and a bicycle pump. Experiment A. The shell is a water bottle. Physical units are given hereby. The water is filled for about 1/3 of the bottle volume, and the air is pressurized up to 3 bar gauge. We start the trial and we observe. What we can meter? Just the flying time, and we get 4.1 seconds. Experiment B. Another water bottle, but something bigger and better shaped. We have now an aerodynamic head and stiff fins. The volume is double, now 2 liters, and the pressure is also higher, 4.5 bar. Also, here we run the experiment. Something higher, and we meter also the flying time, which is now 6.8 seconds. We need to use few different equations now to describe the rocket flight. So first, the cardinal equation of the dynamics applied to the whole body. It says mass times acceleration equals to the sum of the external forces. And which are the forces? We are the weight, the drag, and the thrust. The weight depending upon the mass, the drag upon velocity square, and the thrust upon mass flow and exhaust speed. Let's express in a scalar form, only one-dimensional and vertical. The thrust actually is existing as far as the water is inside the bottle. This is the first equation we need. Then we have another equation, which is given by the thermodynamic and applied to the air inside the bottle. And it says a relationship between the pressure and the volume. What is missing now? The energy conservation applied to the water, also called the Bernoulli equation. It says that the sum of the kinetic energy and the pressure energy is constant between inside and outside of the bottle, always for the water. Inside the bottle, the velocity is negligible and the pressure is equal to the air pressure. Outside the bottle, the pressure is atmospheric and the velocity is the exhaust speed we did in the formula of the thrust. Finally, we use the equation 3, this equation, to get the exhaust speed, VE. They are now missing two equations, which are not any longer physical laws, but just definition. The number 4 is the definition of the mass flow for the water, and the number 5 is the definition of the volumetric flow for the air. After having developed all those equations, there are 5, 3 of them differential, we can resume in a table the sequence in which we need to use them. We start always with the time. Step 0, initial conditions. What we know? We know the velocity, which is 0, the elevation is 0, the initial mass, which is for the whole rocket, is also known. The volume is the initial air volume, so it means the bottle volume minus the water. Then the pressure, which is the starting pressure. And all of them we can meter on side. What about exhaust velocity here? For this, we need to calculate with equation 3. And for the mass flow also, we need to calculate by means of equation 4. Now, step 1. Time is delta time that we can choose. And velocity, we need to use equation number 1. The I is the velocity times delta t, then the mass is the mass before minus mass flow times delta t. For the volume, we need equation number 5. For the pressure, equation number 2. And for VE and M point, we use the same equations as before. And so on. In the table below, we run a real example with numbers. Important is to remember that the condition when the mass lost from the rocket equals the water mass, then the mass flow must be put to 0, and the VE is also 0, so it means there is no thrust any longer. We run now the simulation for the first experiment. All the parameters we need are in the table here on the right side. The drag coefficient we do not know exactly, but we can estimate 0.8. Considering that the bottle in the first experiment is flat, is not well aerodynamic shaped. The curve shows in a range the speed and the altitude in yellow. Speed is increasing the very first fraction of seconds and then is slowly decreasing from here, becoming 0 when the high is the maximum. Soon after, it turns to negative till when the rocket is hitting the ground here. From the chart, we get the flying time, 4.22 seconds, the maximum elevation, 21 meters, and the maximum velocity, 41 meters per second. What we have observed in the experiment was just the flying time, so 4.1 seconds, and it is matching more or less with the numerical development. Repeating the simulation for the experiment B, we input here also all the requested parameters, and as a drag coefficient we put a lower value because of a better aerodynamic shape here. So let's assume 0.3. And our chart shows a flying time which is now longer, about 6.6 seconds. The elevation is also higher, 50 meters, and the maximum speed is 49 meters per second. The time we have metered was 6.8 seconds, so also in this case the model is matching. Are we happy? Not completely. Why? Actually, we could not meter the high experimentally. Since I could not place an altimeter on my rocket, I had been looking for other experimental sources, and I found this German website. There are few flights recorded, and one of them I'm taking here. The flight record says 160 meters of launch height. To run the simulation, we need to input all the given parameters. What is missing once again is the drag coefficient CD. In this case, it is a professional rocket, so I assume better than mine. It must be at least 0.15. What says the result? Exactly 160 meters. Should be CD something worse, still 0.3, we would get 150 meter. So actually not much deviation from it. Now we are happy. Thank you for attendance. Comments or observations are always welcome.